In this video, we're going to talk about how to solve the voltage divider bias circuit. So we're given the values of R1, R2, RC, and RE. And we have an NPN transistor, which you can call Q1. And our goal is to calculate the values of IB, IC, I1, I2, VB, VC, VE, VCE. Basically, we're going to solve the whole circuit. And then we're going to determine if this particular transistor amplifier, if it's midpoint bias. Now we're given the beta of the transistor, it's 200. That's the HFE value. So how can we solve this circuit? The first thing that we want to do is calculate the base current IB. And here's the formula that will help you to do that. IB is going to be equal to VCC, the collector supply voltage, times R2 divided by R1 plus R2, and then minus VBE divided by R2 times R1 over R1 plus R2 plus beta plus 1 times RE. So that's the formula that will help you to calculate IB. Now for those of you who might be wondering, how did this guy get that formula? I'm going to show you how you can derive that formula so you can see it for yourself. I'm not just pulling it out of the air. But we'll talk about that later towards the end of this video. Now let's start by plugging in the values that we have. VCC, the collector supply voltage, is given to us. That is 12 volts. R2, we know it's 20.9 kilo ohms. Now the units will cancel. R2 will cancel with R1 plus R2, so you could write it as 20.9. R1 plus R2, that's 20.9 plus 30, so that's going to be 50.9 kilo ohms. You don't need to change it to 50,900 ohms. VBE, the potential between, let's call this point E, point B for the base of the transistor, and point C for the collector. The difference between the potential at point B and point E is 0.7 volts. That's the voltage drop between the base and the emitter of an NPN transistor. It can vary between 0.6 and 0.7, but in this video we're going to use 0.7. Now R2 times R1. Now for this formula, you want to plug it in ohms, not in kilo ohms. Because R2 times R1 is going to be kilo ohms times kilo ohms, and then R1 plus R2, that's going to be kilo ohms. You're going to get kilo ohms squared over kilo ohms, which won't completely cancel. So for this part of the formula, you need to plug in R1 and R2 in ohms, not in kilo ohms, if you're going to get it right. So R2, we're going to replace that with 20,900 times R1, which is 30,000, divided by R1 plus R2, so that's 50,900, minus beta plus 1. Beta is 200. Add 1 to that, that's 201. And then RE, the resistance at the emitter pin, that is 150 ohms. So make sure to put this all in parentheses, and the same is true for the numerator if you're going to type it straight in your calculator. So let's go ahead and plug this in, and let's see what answer we're going to get. Now, I almost made a mistake here. That should be a plus sign, so let's make that correction. So give me a minute while I plug this in. So the answer that I got for the base current is 9.954 times 10 to the minus 5 microamps. I mean, not microamps, but amps. If we multiply that by 1,000, that gives us a base current of 0.0995 milliamps, which, if we want to, we can round it and say that's approximately 0.1 milliamps, just to make our future calculations a lot easier. That's very close to 0.1 milliamps. So that's IB. So let's make a little note here. So the current flowing into the base, that is conventional current. The direction of electron flow is opposite to the direction of conventional current flow. So that base current is 0.1 milliamps. Now our next step is to calculate the collector current. The collector current is equal to beta times the base current. So beta is 200, and let's use the base current of 0.0995 in this case. Well, technically 0.09954 milliamps. So 200 times that number gives us a collector current of approximately, it's 19.908, but we're going to round that to 19.9 milliamps. So that is the collector current. So that's the current that is flowing through RC. So that's 19.9 milliamps. So now we can calculate the emitter current. The emitter current is going to be IB plus IC. So IB is approximately 0.1 milliamps. IC is 19.9. So the emitter current is going to be approximately 20 milliamps. Now let's clear away a few things just to have some extra space to write stuff. So now that we know the emitter current, we can calculate VE. VE, the potential at point E, is basically the voltage drop across RE. So it's going to be IE times RE. So we have an emitter current of 20 milliamps and an emitter resistance of 150 ohms, but we're going to convert that to 0.15 kilo ohms. When you multiply amps by ohms, you get the unit in volts. When you multiply milliamps by kilo ohms, you get the unit in volts as well. So we can do 20 milliamps times 0.15, or you could say 0.02 amps times 150. And in both cases, you're going to get 3 volts. So that is the potential at point E. So right now, we have the values of IB, IC, and VE. So now let's get VB. VB is going to be 0.7 volts more than VE. So 3 plus 0.7, that will give us a voltage of 3.7. So I'm going to write that here next to point B. So that's the potential there. Now let's calculate the potential at point C. The potential at point C is going to be the collector supply voltage minus the voltage drop across RC, the collector resistance, or the resistor associated with the collector pin of the transistor. So that's going to be IC times RC. So VCC is 12. We know that the collector current is 19.9 milliamps. The collector resistance in kilo ohms is 0.15 kilo ohms. So it's 12 minus 19.9 times 0.15. And so VC is 9.015 volts. We can approximately say that's 9 volts because for these two, we've rounded it to the nearest tenth, at least for VB. So rounding this to the nearest tenth, that's 9.0, which we could say it's 9 volts. So I'm going to put that here. So now that we have VB and VC, what's next? The next thing we need to do is calculate I1 and I2. It's better to calculate I2 first before you calculate I1. Well, in actuality, you can do it in any way, so it really doesn't matter. I'm going to calculate I2 first. I2 is going to be the voltage across it, which is 3.7 with respect to ground. and ground is going to be 0 volts. So the voltage across R2 is the potential at B divided by R2. That's going to give us the current flowing through R2. So Vb is 3.7 volts. R2 is 20.9 kiloohms. Now keep in mind, when you divide volts by kiloohms, you're going to get the current in milliamps. So 3.7 divided by 20.9 gives us a current of 0.177 milliamps. So let's write that here. And let's highlight that in red. So now let's think about this point, which is equivalent to point B. So at that point, we have a current of 0.177 milliamps going in that direction, and a current of 0.1 milliamps leaving that junction as well. So the current that's entering this junction, point B, is the sum of those two currents. So we could say that I1 is the sum of I2 plus the base current. So that's 0.177 milliamps plus 0.1 milliamps. That gives us a current of 0.277 milliamps. And so that's I1. Now let's check our work to make sure that we've done everything correctly up to this point. According to Kirchhoff's voltage law, especially for DC circuits, the voltage around a closed loop must add up to 0. In this case, the voltage across R2 and R1 should equal the difference between those two values. It should equal 12, the collector supply voltage. So we could say that V1, the voltage across R1, plus V2, the voltage across R2, should be equal to VCC if we did everything correctly. So the voltage across across R1 is going to be I1 times R1 according to Ohm's law. And V2 is I2 times R2. So I1 is 0.277 milliamps, and R1 is going to be 30 kiloohms. I2 is 0.177 milliamps times R2, which is 20.9 kiloohms, and that should equal 12 volts. So 0.277 times 30 plus 0.177 times 20.9, that's equal to 12.0093, which is approximately equal to 12. And so this tells us that our math is correct. Everything that we have is good. Now the next thing that we need to do is determine if the transistor amplifier shown below is midpoint bias. It's going to be midpoint bias if VCE is 1/2 of the collector supply voltage. So let's find out what VC is. VCE is the difference between VC and VE. So VC is 9 volts, as we can see here, and VE is approximately 3 volts. Keep in mind, VC is like 9.015, but for all practical purposes, it's close to 9. So VCE is very close to 6. So we could say that within reason, this particular circuit is midpoint bias. Now let's talk about how we can derive the formula for IB. So we said that IB is equal to VCC times R2 over R1 plus R2 minus VBE divided by R2 times R1 over R1 plus R2, and then plus beta plus 1 times RE. Because this formula was very useful in helping us to calculate the base current. So let's understand how we can derive that formula. So here we have an equivalent circuit of the circuit that we had before, just without the capacitors. Now, what we need to do is draw the Thevenin equivalent of this portion of the circuit. So here's what we can do. This is going to be the voltage source, and this is going to be the Thevenin resistance, and then we're going to connect that to the base and the emitter part of the transistor, and then we have the emitter resistance, because that's the part of the circuit that we need to focus on to calculate the base current which flows through the Thevenin resistance, or the equivalent Thevenin resistance. And this is going to be V Thevenin. V Thevenin is not the same as 12 volts, by the way. Now, according to Kirchhoff's voltage law, we can write the following equation, starting from this section. As we go from the negative terminal to the positive terminal of the voltage source, that's going to be a voltage rise, so that's plus V Thevenin. As we travel through R Thevenin, the voltage drop is going to be negative IB times R Thevenin. The resistor consumes energy in the circuit, so it's going to be a voltage drop. The transistor also consumes energy, so we're going to have a voltage drop of VBE, and the resistor consumes energy as well. And so we have IE flowing through RE, so it's going to be minus IE times RE. And according to Kirchhoff's voltage law, the sum of the voltage drops will be 0. So we have V Thevenin minus IB times R Thevenin. VBE, we set that to 0.7 volts. Now, IE, the emitter current, is the sum of the base current plus the collector current. Now, the collector current, we can replace that with beta times IB. Let's erase this for now. So what I'm going to do at this point is factor IB from this part of the equation. So we have V Thevenin minus IB times R Thevenin minus 0.7, and then minus IB, and then it's going to be beta plus 1 times RE, which equals 0. Now what I'm going to do is I'm going to take these two terms and move it to the right side of the equation. So at V Thevenin minus 0.7, that's going to be equal to IB R Thevenin plus IB times beta plus 1 RE. Now the next thing I'm going to do is factor out IB. So I'm going to have R Thevenin plus beta plus 1 in parentheses times RE. Next, I'm going to divide both sides by R Thevenin plus beta plus 1 times RE. So these will cancel on that side. So now I have this formula. IB is equal to the Thevenin voltage minus 0.7 divided by the Thevenin resistance plus beta plus 1 times the emitter resistance. Now how can we calculate the Thevenin voltage? Because it's not equal to the collector supply voltage. Well, first we need to draw a circuit disconnecting this portion of the original circuit that we had before. Let's call this point A and point B. So in the original circuit, we had a power source and we had two resistors, and this would be point B and point A, which was attached to the base of the transistor and the ground where the emitter resistor was. So we need to calculate the voltage across R2. This is VCC, and the voltage across R2 will be the Thevenin voltage. So this is basically a voltage divider circuit. So the Thevenin voltage is going to be R2 divided by R1 plus R2 times the collector supply voltage. And so that's what we're going to replace V Thevenin with in this formula. So that's where we get that part of the formula from. It's from the voltage divider network that is formed from R1, R2, and VCC. So now the next thing we need to do is calculate the Thevenin resistance. In order to calculate the Thevenin resistance, replace the voltage source with a short circuit, and then calculate the equivalent resistance between points A and B. So R1 and R2 are parallel to each other with respect to points A and B. Therefore, because they're parallel, we could say that the Thevenin resistance, which is the equivalent resistance of the circuit at point A and B, that's going to be R2 times R1 over R1 plus R2. So now putting this together, we can write our final equation. So now we just got to replace R Thevenin and V Thevenin. So the base current is going to be V Thevenin, which we said is VCC times R2 over R1 plus R2 minus 0.7. And then replacing R Thevenin, we have R2 times R1 over R1 plus R2, and then plus beta plus 1 times RE. So that's the formula we need in order to calculate the base current of the of the voltage divider bias circuit.